Okay, a quick revision on what we did in the last class. I started with fluid mechanics, and I said that fluid mechanics is a branch of physics or a branch of science that has to do with fluid being at rest or in motion. We practically study the conditions of fluid at rest or the properties that um, a fluid possesses when it is at rest. Also, we also study fluids in motion, but the main thing we did in the last class was just hydrostatics, which is the study of what fluid at rest. Fluid statics is divided into two: hydrostatics and aerostatics. The same thing for fluid dynamics, hydrodynamics and aerodynamics. Hydro has to do with liquid, as aero is to gases. For hydrostatics, it is the study of fluid at rest. Then I made mention of some um, subtopics on fluid statics, such as density and relative density, capillarity, pressure in fluids, and surface tension. For density and relative density, I gave a quick highlight for which I explained density as the mass per unit volume of a substance, that is, the mass which 1 meter cube of a substance possesses should be termed the density of that substance. So density is usually denoted with the symbol rho, and it is given as what? Mass over volume. Then we have relative density, which happens to be the ratio of the density of a substance to the density of another substance, meaning we compare one density to another. But water happens to be a universal solvent, so it is commonsensical to take water as a reference standard. So we have a measurement of density and RD, Uptrust, Archimedes principle, flotation principle, then we solve problems. So last class we were able to take 1 and 2. So in today's class we'll move into Uptrust and Archimedes principle. So this was still part of last class. Density being mass over volume. Like I said, the symbol for density is rho. So we have rho equals to m over v. M is the mass, v is what? The volume. Density for water is 1000 kilogram per meter cube, or 1 gram per centimeter cube. I talked about conversion of density from gram per cm cube to kilogram per meter cube and vice versa. 1 gram per cm cube is equal to 1000 kilogram per meter cube. This is the proof below here. So density of common substances for water is 1000 kilogram per meter cube, which is also 1 gram per cm cube. For mercury, it is 13,600 kilogram per meter cube approximately, or in gram per cm cube that will be 13.6. So you can see that mercury is more than 13 times denser than water based on what you can see. Relative density, density of a substance over density of water. It is also called specific gravity. You can shorten it to RD or SG. RD will mean relative density, SG would mean specific gravity. You shouldn't expect it to have a unit since it's a ratio of two densities. So this is me talking about the density of a mixture. While you can add up masses of things that you mix together, and also volumes of things that you mix together, you cannot add up their densities. So you need to get their densities separately, saying density of the mixture is mass of the mixture divided by the volume of the mixture. So this is a particular question we solved in the last class, which we got 0.75 by finding the density of the mixture. So if you missed the last class, please just check the what's it called, the video of the recorded class in the last class. All right. So then I gave other formulae for determining the relative density of a substance, which can be, the general formula is density of a substance over density of water. Then we have it can also be mass of a substance. Now it's very important you look at the word equal volume here. You can't just say density is mass of a substance over mass of water. It would be wrong. It has to be mass of a substance over mass of equal volume of water. This is the proof below here. Okay, another formula for density being weight of the substance in air over upthrust in water. This is used for determining density, relative density of a solid substance. Weight in air is WA. Upthrust in water means weight in air minus weight in water. That's simply WA minus WW. Then determination of the relative density of a liquid. So in this case, if you were to be a student in the lab and you were to find the relative density of a certain liquid, you can get a certain object. You immerse it in the liquid and you determine the upthrust of that substance in the liquid. You do the same thing in water. You determine the upthrust of that same substance in water. The ratio of the two upthrusts will reveal the value of the relative density of that liquid. And since upthrust is weight in air minus weight in the liquid, so we have WA minus WW divided by what? WA minus WL divided by WA minus WW. Okay, so let me quickly add somebody to the class. Alright, so this is an example where a question provides the weight of a substance in water as 20 newtons, the weight in a certain liquid X provided as 30 newtons, and the original weight of the object in air provided as 40 newtons. Question wants you to determine the relative density of the substance. So this is the approach. I don't need to go through this again. Like I said, go through the last video. This is also another question. This is like an application question telling you that a liquid X of density 900 kilogram per meter cube and water of density 1000 kilogram per meter cube are mixed together, but they remain what? Immiscible. Okay, there's a wrong spelling of immiscible. Okay, the question is asking which of the two liquids will stay on top. When you mix two liquids that are not mixable together, the one of higher density always stay below, while the one of lower density stays on top. So for instance, when you mix water and this particular liquid, water has 1000, this liquid has 900, so liquid X is going to stay on top. That explains why a liquid like petrol, when mixed with water, stays on top, water stays below. No matter how small water is, you drop a tiny molecule of water into a large container of kerosene, the molecule of water will still go all the way down to the bottom, because water has a higher density than kerosene or petrol. This is also another application question. We don't need to go into that. Now, we talk about methods for determining the relative density of a substance. The RD bottle, U-tube, airs apparatus, hydrometer, which happens to be the fastest approach. Then we have the lever balance. The RD bottle utilizes the concept of equal volume of water or equal volume of the substance. Because you are using a certain bottle, if you fill it up with a certain liquid, it's going to have the same volume as filling it with water too, because both of them will be filled to the same mark. So that's like a guarantee of equal volume. So how do we utilize an RD bottle? It always begins with measuring the mass of the empty bottle. When you are done with that, you then fill the bottle with let's say a certain liquid X. You measure the total mass. That is not the original mass of the liquid. To now get the mass of the liquid, you have to subtract the mass of the bottle. Once you are done with that, you empty the container again, and fill it with water. You measure the total mass of the water and the container. You also get the mass of the container, mass of the water from there, just like you can see here. Right? So when you are done, you can use that formula that says RD equals the mass of a substance over mass of equal volume of water. Like I said, equal volume has been guaranteed by using the RD bottle. So from there, you have that. So this is like a question we solved in the last class that says there is an RD bottle that has a mass of 20 gram. When filled with water, the weight should be more than 20 gram, right? So in this case, it's 35 gram. Similarly, when filled with a certain liquid X, the weight is 30 gram. So based on what you can see, when you fill it with water and the weight is 35 gram, when you subtract 20 from 35, that gives you 15. That accounts for the weight of water. And when filled with 30 gram of liquid X, subtract 20 gram from that, that is going to be 10 gram of liquid X. So using the formula mass of liquid X over mass of equal volume of water, you have 10 gram over 15 gram. So that tells you that the liquid is 0.667 in terms of relative density. In terms of relative density, we have that as the liquid. So similarly, a question can ask you for the density of this liquid. I need to emphasize something. From RD being density of a substance over density of water, we can tell that density of the substance is going to be relative density of that substance times density of water, right? So now imagine that this is RD. We all know that relative density, the density of water is 1 gram per cm cube. So which means multiplying 1 times RD will just give you RD. What do I need you to get from this statement? If you have the RD of a substance, automatically you have the density of that substance in gram per cm cube. Like this substance now, it has an RD of 0.667 I can also tell you that it has what? A density of 0.667, but in gram per cm cube. Don't forget, ROD has no unit, but density itself has a unit. So ROD of this substance is 0.667, then the density of the substance is also 0.667, but you have to now put a unit of gram per cm cube. Please take note of that. ROD of water is 1. Density of water is 1 gram per cm cube. ROD of mercury is 13.6. Density of mercury is 13.6 gram per cm cube. Alright, moving on. We talked about a hydrometer. Two liquids, X and Y, are in two different containers but filled to the same level. We want to be able to use a hydrometer to tell the story of its density. Okay, a denser liquid is going to give a level of resistance to object that wants to penetrate them. So you expect a hydrometer to go deeper in a less dense liquid compared to a denser liquid. So looking at this particular diagram here for liquid X and Y, you can tell that the hydrometer goes deeper in X, and it's not as deep compared to what? In Y, you can see that it's not as deep compared to X. So just by that eye inspection, you can tell that liquid Y is denser than X. Because if you are denser than me as a liquid, you will not allow things to go deeper in you. Okay, so this is me giving a relationship between the depth of a liquid, the depth of a hydrometer or of a substance in a liquid compared to its density. It is an inverse proportionality. The more the density of the liquid, the lesser the depth of the substance in the liquid. So this is an example to pass the message across better. From what you can see here, we have two densities, one with 0.8 gram per cm cube with the other with 0.9 gram per cm cube. We did a simple calculation using H1 rho 1 equals to H2 rho 2, this formula here. We're able to get the depth in the second liquid to be 16 compared to the one of the first liquid, which is what, 8. This is a testament that a liquid goes deeper in a less dense, an object goes deeper in a less dense liquid. You get that? So this is me explaining YouTube. How you use YouTube to determine the density or the relative density of immiscible liquids. The first thing you want to do is you want to fill it with, for instance, water. When you fill it by pouring the water from one arm of the U-tube, it fills the other parts of the U-tube and they will be at equal height. So once you are done with that, the next thing is to fill it with a certain liquid, whose relative density is what you are looking for. You keep doing that until you have a height difference. So you record the height H1 at the left hand side and the height H2 at the right hand side. So based on what you can see here, we can then say H1 rho 1 equals to H2 rho 2. Okay, for instance, okay, before we go to S apparatus, let me quickly explain something here. Let's duplicate. Okay, good. So you have, say we have water versus liquid X. So we can say H1, H water rho water, that's the height of water versus the density of water, should be equal to the height of liquid X, let me use L, and what? The density of the liquid L. From there, if we choose to make rho L over rho W, that is density of the liquid over density of water, the subject, what this will turn to is HW over HL. Please, it's not going to be HL over HW. The arrangement must be such that when you cross multiply, you get what you had before. And this expression is meant to be relative density of the liquid. So relative density of the liquid can be density of the liquid over density of the water. That's if you have densities. But if you don't have density, in this case you have height, it's going to be height of the water over what? Height of the liquid. So this is how you use the U-tube to determine the relative density of a liquid. And mind you, you use what? U-tube for finding the relative density of immiscible liquids. Then we have something similar here, which is called the S apparatus. The S apparatus is used for determining the relative density of liquids that can actually mix together. Because we are aware that the liquids can mix together, we want to try our possible best so that they won't have a contact, because for them to mix they need to contact themselves. So in this case, we try to put the two liquids in different containers, like in this case labeled container 1 and container 2. So what do? In this S apparatus, it seems like a U-tube that is inverted. Here you have a tap. Through this tap, you can suck out air. When you suck out air, liquid rise from container 1 and container 2, as you can see in the diagram. So you record their respective height H1 and H2. You may not be able to do this simultaneously when you are sucking out the air. Once you have sucked out the air, close the tap so that the air will not return back. So this will help you to retain the height of the liquid in the tubes. Then you measure H1 and H2. Similarly, you do H1 rho 1 equals to H2 rho 2, just like you did in U-tube. Alright, so we'll move into the next section from here. Okay, I think this was where we stopped in the last class. So today we are gonna pick it from there. Alright, we're done. Let's create more space. Yep. So upthrust. So two things you can pick from the word upthrust. Up. Then you have what? Thrust. Up, it means going up, right? Thrust is a force. So just like we have upthrust, we can also have what they call downthrust. So upthrust is a force experienced by an object immersed in a fluid. When you immerse an object in a liquid or in a gas, there is always an upward force experienced by that object due to the liquid. Such force is called what? The upthrust. It is denoted U, and it is also called buoyancy. Or you call it what? The buoyant force. Is it B-O-U or B-U-O? Wait, buoyancy. I think it should be what? B-U-O. Does it sound? See, please check it out. So it could be buoyant force, or you call it buoyancy. So when a question say you should explain the buoyant force, indirectly the question wants you to explain upthrust, and you simply say it is the upward force experienced by an object in mass in a fluid. Okay, now say we have a liquid in a container. This is a container. This is a liquid in a container. You have an object in mass in the liquid as shown in this diagram. This is an object immersed in the liquid. Okay, what are the things we can experience here? There will be a tension in the string, tension T. There will be a weight acting downward. That's the weight of the object. Weight equals to mg. Now there is now a force acting upward within the fluid, and that is exactly what we describe as what? Upthrust. Okay, so from here we have two forces, T acting upward. T is the tension in the string. U acting upward. U is the upthrust, and we then have another force, weight, W or mg, acting downward. Usually we also have a force called the viscous force, but in this case we need to neglect it. We need to assume that the viscous force is negligible. So if there is an equilibrium for these forces, we should expect upward force should be equal to the downward force. So in this case, it is going to be U plus T equals to what? Mg. Now if you connect this, for instance, if this had been connected to a scale balance, or let's say it is connected to a spring balance. This is spring balance here. Okay, this is a spring balance here. We have the calibration of the spring balance. Okay, so before you immerse the object inside the liquid, what it was recording then was just the weight of the object, the weight in air of the object. Okay, then by the time you insert it into the liquid, what it will now be recording would be called the apparent weight of the what? Of the object. The apparent weight of the object. Okay, so in this case our upthrust is going to be equal to what? Mg minus tension in the string. So this is like saying this mg is the original weight of the object, which is called the weight in air. Then this tension is no longer the weight of the object it is recording. It is recording, let's call it the fake weight of the object, which is specifically called the apparent weight of the object. That is the weight of the object while inside the liquid. So if the weight of the object before you insert it into the liquid is denoted WA, which means weight in air. The one while in the liquid, let's call the liquid water, is going to be what? WW. So this is how we arrive at upthrust being weight in air minus what? Apparent weight in the liquid. So always take note of that. Upthrust equals to weight in air minus weight in liquid. So if the liquid is water, we have WA minus WW. Okay. Now this is a case when the object is at equilibrium. We can also have situation where the object is not at equilibrium. The object might be practically accelerating within the fluid. Okay, so in that case, we can find the resultant force and equate to ma, which is mass times acceleration. So if, for instance, the object is going down, is going towards the bottom, the net force is going to be mg minus bracket open t plus u. Then we can equate it to what? Ma. This is when the question gives you information like acceleration, etc. But for now, we are not interested in that. Alright, that's how you get what? Upthrust. Quiz. The weight of an object is 100 Newton in air. Without putting this in air, by default you should still take it as weight in air, except the question now means something else. While its apparent weight, apparent weight here is like the fake weight of the object, which means the weight of the object in the fluid, while the apparent weight of the object, while its apparent weight, I've already used it, is 80 Newton. What is the upthrust? What is the upthrust experienced by the object? Experienced, let me rewrite that. Experienced by the object. Okay, can somebody tell me what the upthrust would be? Anybody? What's the upthrust? I'm listening. Who is talking? I can't hear you. Upthrust is what? Say that again. Did you say 50 Newton? No, that is wrong. Well, the weight in air of the object is 100 Newton, and the apparent weight of the object is 80 Newton. Good. You are right. The upthrust is what? 20 Newtons. So the upthrust is 20 Newtons. So you say U, which is upthrust. Some texts use B. B for buoyancy. Okay. We have 100 Newtons minus 80 Newtons. So that gives us what? 20 Newtons. So upthrust will always be weight in air minus weight in the liquid. You get? Apparent weight in a liquid. Okay, so that is how you obtain upthrust. That's the main definition of upthrust: the upward force experienced by an object when immersed in a fluid. All right, that takes us to the next, which is the Archimedes principle. The Archimedes principle. Okay, this is a principle that governs what happens to object when you immerse the object in a fluid. Now, imagine we have a container here. So we have this to be a container, and inside the container we have what? A liquid. Okay, now let me do. Okay, we have a liquid. This happens to be the level of the liquid, and then you have an object immersed inside what? The liquid. This kind of immersion that you can see in the diagram is called partial immersion. We can as well have what? This immersion. This one is called what? It's called complete immersion. So when these two things happen, either partial immersion or complete immersion, you know, we have already agreed that there will be an upthrust, an upward force exerted on the object. So what Archimedes' principle did was to redefine upthrust. It's telling us that what? The upthrust experienced by the object will always be equal to the weight of the liquid displaced. I repeat, when an object is partially, let me write that, it states that when an object is partially or totally immersed in a fluid, it experiences an upthrust. It experiences an upthrust which is equal to the weight of the fluid displaced. Weight of the fluid displaced. The bottom line here is upthrust equals to what? Weight of fluid displaced. Weight of fluid displaced. So anytime you are being asked of Archimedes' principle, this is the main thing. Every other thing is story. Upthrust experienced by the object will always be equal to the weight of the fluid displaced. Let me try explain that with a diagram. You have a container. This is a container. Then in the container you have okay, let this be a special container called the Eureka can. This is a Eureka can. Now, if you, no matter how much you intend to fill this container, because of this pathway, the liquid will always what? live through that hole so as to always maintain a certain level of a liquid here. Okay, so you have a Eureka can here. It has been filled to this point here, to this particular level here. Definitely, when you immerse an object in a fluid, either partially or completely, it takes some space in the liquid by displacing liquid. So the implication here is that it's supposed to displace fluid from initial level to a new level. So because there is a hole in this particular container, the extra liquid that got displaced can be collected in a different container beside it. So this is the container beside it for the collected liquid after immersion. Okay, so what do we have? This will be called liquid displaced. Liquid displaced. So we have upthrust, which is the upward force experienced by the object U. What Archimedes is telling us is that when you measure the weight of the liquid displaced, let's call that WLD. The LD represents liquid displaced, would be equal to the upthrust. So upthrust equals the weight of liquid displaced. So it's telling us that experimentally, if you find upthrust by the usual approach of finding upthrust is saying weight in air minus weight in liquid. When you get the result for upthrust and you also decide to get the result for the weight of liquid displaced by measuring it on a scale balance, the two values will be competing, they will be equal. The upthrust is equals to weight of liquid displaced. Please take note of that. Upthrust equals to weight of fluid displaced. Take note of that, irrespective of what? Partial or complete immersion. Okay, let me quickly address something. Complete immersion versus partial immersion. Okay, say we have this to be a container. Let's draw that well. Okay, this is a container, and we have this to be a liquid. Then we have these to be, hold on. We have this to be an object immersed in it. This is a complete immersion. Now let's take part of this. Control V. Okay, now we want to explain what a partial immersion is. Good. Something like this is a partial immersion. Can you see that? Complete immersion versus partial immersion. According to Archimedes, for both cases, upthrust will always be equal to weight of the liquid displaced, either complete immersion or partial immersion. But here, the volume of liquid displaced here, liquid displaced, in this case, volume of liquid displaced is equal to volume of object. Volume of liquid displaced, V0 is volume of object. Volume of liquid displaced equals volume of object, since everything was completely immersed. But here, volume of liquid displaced is going to be less than volume of object. Why? Because not all the object was what? Immersed. This is the only part that is inside water. So in this case, volume of liquid displaced is only equals to the volume submerged. Volume submerged, meaning the shaded part was the only part that displaced liquid. Please take note of that, because when we are solving problems, I will make use of this information. So for instance, if what we have here is, let's say, 1/4, so I can say volume of the object, the volume of the object inside the liquid, that is this volume submerged, is just going to be 1/3 of the total volume, and this is what will be equal to the volume of the liquid displaced. Always take note of that, please. All right, before we solve some questions, let's just go straight to principle of flotation. All right, flotation principle. Flotation principle. So flotation principle was also stated by Archimedes. In advanced text, what you are going to see is Archimedes principle 1 and Archimedes principle 2, which means the principle 1 is the one that we have already stated, that when an object is partially or totally immersed in a fluid, the upthrust experienced by the object is going to be equal to the weight of the fluid displaced, while the Archimedes principle 2 now is the flotation principle. It's giving you reason why object floats. So an object floats when it displaces some fluid, or in this case let's use liquid. An object floats when it displaces some liquid whose weight is equal to its own weight. Let me rephrase that. If you remember from Archimedes principle 1, upthrust equals to weight of liquid displaced. In flotation principle, it's telling you that an object can only float if the upthrust is equal to the weight of the object. Alright, let me write it down. It states that an object floats if the upthrust, let me be more specific, an object floats in a fluid or in a liquid if the upthrust experienced by the object due to the liquid is equal to the weight of the object. Okay, now let's use the same diagram here. So when we are talking about flotation principle, we really make use of suspensions. The object has to be there on its own accord. Now see this. This is an object floating on a liquid. We have two major forces we should be looking at here: the weight of the object, which is acting down, and the upthrust experienced by the object due to the liquid, which is acting up. Just by what you can see, if the downward force, which is the weight, is more than the upward force, we expect the object to continue going down, right? And if the upthrust is bigger than the what? Than the weight. If the upthrust is bigger than the weight, though the object will still float, but it's going to wander easily on the what? On the surface of the liquid. The object will be so fluffy on the surface of the liquid. Well, it's still floating in a way. So, but we are giving the smallest condition for flotation to happen. At least the upthrust U must be equal to the weight of the object. Upthrust must be equal to weight of object. That's the principle of flotation. Upthrust equals to weight of what? Object. That's what we have here. And recall, upthrust itself, according to Archimedes principle 1, upthrust is equal to weight of liquid displaced. Therefore, we can say that since upthrust is now equal to what? Weight of object for flotation to happen. Please, this principle, you cannot just use it anyhow. You have to be sure that there is flotation, or the question has to be particular about flotation before you can equate upthrust to weight of object. If the object is not floating, or if you are not conditioning an object to float, and you go ahead and use upthrust equals to weight of object, you are completely on your own. So what we have is upthrust being weight of object and also being weight of liquid displaced. You can say weight of liquid displaced is equals to weight of the original weight of the object at flotation. Let me put the condition there, at flotation, because without flotation, when you write that, that would be completely wrong. You get that? So the object has to be floating for you to use the statement. Alright, so we can solve some examination problems. Okay, let me quickly emphasize something. NB from Archimedes principle. We have it that upthrust experienced by an object must be equal to weight of the liquid displaced. We can break this down further. Since weight is mg, so we can say mass of liquid displaced times what? G. We can still break it down further. Recall that density is mass over volume. From here, when you cross multiply, mass is going to be density times volume. So this mass of liquid displaced can be replaced with density of the liquid times the volume. You can't just say of the liquid there, it has to be of the liquid displaced if you are referring to the volume, because this mass of liquid displaced times G. So it is either the question simply gives you the weight, or gives you the mass, or gives you the volume of the liquid displaced. Now, it is very, very rare the question gives you the volume of the liquid displaced. The question will leave you to deduce it out yourself. Okay, how? Let me go back to this that I explained. It is important you know that complete immersion is different from partial immersion in terms of looking for volume of liquid displaced. At complete immersion, the volume of liquid displaced is exactly the volume of the object, because of course the object was completely immersed, so its full volume was what displaces the liquid out of position. In the second case, partial immersion, the volume of liquid displaced is not equal to the volume of the object. In fact, it is less than the volume of the object. So it is not left for the question to give you information like 1/3 of the object was immersed, or 2/3 of the object was immersed, or it can tell you that 1/4 of the object was immersed, or it can also use statement like 1/3 of the object remain outside the liquid. If 1/3 remains outside the liquid, it means what? 2/3 was immersed. Now you need to use your common sense to deduce that out. So volume of liquid displaced here is going to be equals to volume of object, this at complete immersion, or you say volume of liquid displaced equals to volume submerged, volume of object submerged. Partial immersion. So please take note of that. While we are solving problems, it would matter. Alright, I'll pick some examination problems. Just hold on, let me bring out some questions on that. Let's see. Just hold on, let's check some problems. It's currently loading. So while it loads, I need you to look at this problem. Examination problems. Okay, 1. An object of mass 10 kilogram was partially immersed in a liquid of density 1000 kilogram per meter cube. So if the volume of the object is 2 meter cube, and 2/5 of the object was immersed in the liquid. Determine the upthrust experienced by the object. Take G to be 10 meter per second square. So I want you to attempt it. I want you to attempt that. So I'll give you like a minute to do that. So let me give options. Option A, you have 10,000 newtons. B, 8,000 newtons. C, 6,000 newtons. D, 80 kilonewton. E, none. So I want you to attempt that. Okay, I'll give you 30 seconds more for that. Alright, so what did anybody get there? Okay, no one provided an answer there. Okay, I'll solve it. The answer should be what? 8,000 newton. Let's do that together. So according to the question, it says that you have an object of mass 10 kg was partially immersed in a fluid of density. The density was supplied as 1,000 kilogram per meter cube, and the volume of the object is supplied as 2 meter cube. And the question said to 2/5, 2/5 of the body was immersed in the liquid. We are looking for the upthrust experienced by the object. You use what was it called? You make use of Archimedes principle here. Archimedes principle states that what upthrust is equal to weight of liquid displaced. So this is going to be mass of liquid displaced times G, and this is also equals to density of the liquid, volume of the liquid displaced times what? G. Density of the liquid, you have it. This is what? 1000. Now you also need volume of the liquid displaced. You have volume of the object. Now look at this. 2/3 of the object, 2/5 of the object was immersed. So volume of the liquid displaced is going to be 2/5 times 2. Then G, you know what it is. So in that case, we can say that density of the liquid, which is 1000, times volume of the liquid displaced, which is going to be 2/5 times what? 2. Then times 10. So what does that give you? That give you 5 in 10, that's 2. 2 times 2 times 2, that's 8. So that gives you what? 8,000 newtons. So the result is 8,000 newton. Now the mass given to you here is not going to be needed here. Like, we don't need the information here. So that's how you solve this particular problem. Okay, I'll twist it a bit. I'll twist the same question. Question 2. Question 2. An object of mass 5 kg and density 2000 kilogram per meter cube is immersed completely in a liquid of density 800 kilogram per meter cube. 800 kilogram per meter cube. Take G equals to 10 meter per second square, comma, determine the upthrust experienced by the object. So I want you to attempt that. Attempt that, please. Okay, let me supply options. Option A, 20 newtons. Option B, 30 newtons. Option C, 200 newtons. Option D, 50 newtons. Option E, none. Say that again.
My answer is
50 newtons. Okay, somebody got 50 newtons. Let's find out if that's correct. Any other person? Okay, let's move on. We need upthrust. To find upthrust, whenever a question asks you to find upthrust, there are two ways. It can be from the original definition of upthrust, weight in air minus weight in liquid. Obviously, this is not what we're going to use in this case. The second case is Archimedes principle. Upthrust equals to weight of liquid displaced. So when you're looking for upthrust, two ways, either by the definition of upthrust itself or from Archimedes principle. So upthrust equals to weight of liquid displaced, mass of liquid displaced times G, which is density of liquid, volume of liquid displaced times G. Density of the liquid, we have it, this is it here, 2000 kilogram per meter cube. G, we have it, this is it here, 10 meter per second square. What's delaying us right now is volume of liquid displaced. Now, how do we know what volume of liquid displaced is here? Now, look at this. This statement says it all. Immersed completely. Since the object was immersed completely, it means the volume of the object must be equal to the volume of liquid displaced. So, from density equals to mass over volume, volume should be equals to what? Mass over density. So volume of the object is going to be equal to mass, which is 5 kg, over density, which is 2000. Is it? No. Hold on. The density I was referring to here, the density in this formula here is not 2000. The density of the liquid is actually what? 800. What they gave us 2000 is the volume, density of the object itself, kilogram per meter cube. So knowing the volume now, this should also be equals to volume of liquid displaced is equals to volume of object at complete immersion. So what do we say? The upthrust is going to be, what's the density of the liquid? Is given as 800. Then times the volume of liquid displaced, same as volume of object in mass, that's 5 over 2000. Then times G is 10. What do? You simply say 800 times 5 divided by 2000 times 10, that gives us what? 20 newtons. So the answer is not 50, the answer is what? 20 newtons. 20 newton is the upthrust experienced by the object. Now let's pick a question from a test. Okay. So from a textbook, we have some questions. Let me screenshot that for you. One, two, three, 4, 5, 6. Okay, this should be legible enough at your end. Look at this question. We have crude oil of volume 600 centimeter cube has a density of 0.9 gram per cm cube. Then when heated, the density of the oil decreases to 0.6 gram per cm cube. You're looking for the volume of the heated oil. I need you to attempt it first. I'll give you 40 seconds for that. 40 seconds. Thirty seconds. Time up. 40 seconds is over. Nobody got that. Okay, now let's do it together. Crude oil, they gave you volume. This like V1 equals to 600 centimeter cube. Density 0.9 gram per cm cube. And they said the density actually changed when heated. So that's the second density, rho 2, given as 0.6 gram per cm cube. So the question is asking to find V2. Okay? By looking at this, I can tell that the answer is, just by inspection, I can tell the answer is 900. Let's find out. Density is what? Mass over what? Over volume. Okay, the only thing that's going to be kept constant here is mass. Mass is density times volume. So we can say rho 1 V1 equals to rho 2 V2. You need V2. So V2 should be equals to rho 1 V1 divided by what? Rho 2. Rho 1 is given as 0.9. V1 is given as 600. Rho 2 is given as 0.6. So just by looking at that, the answer is going to be 900 cm cube. So the answer to that is 900. I'm going to give another question. I'll give another question. This question will be for 30 seconds, so be on the alert. It's gonna be for 30 seconds, just 30 seconds. Be on the alert. Okay, look at that. That's 30 seconds. I'll start counting now. What is happening? 30 seconds, no answer. What is happening? I'll give 10 more seconds. Like, this is a very simple question for you not to have an answer to. So, who has gotten the answer to that? Let me know. You say what? silver. Okay, let's find out. Does any other person have something else? You got copper as the answer. All right, let's find out. Let's find out. So, according to the questions, they supplied, they said the relative density of gold, silver, copper, and zinc are given as 13, sorry, 7, I mean 19.3, 10.5, 8.9, and 7.1, respectively. A piece of ornamental metal weighs 0.5455 kilogram and displaces 5 exponential minus 5 meter cube when completely immersed in water. The question is asking the the metal. You have one job is to find the density of the metal and compare what you get to the table of density or to the density supplied to us. Density is mass over volume. The mass of the metal is given as 0.445 kilogram. Though the density of the metal was not given, but according to the question, the metal displaces fluid, displaces a liquid of 5 exponential minus what? 3, minus 5, which happens to be the volume of the object itself. Don't forget that on complete immersion, volume of liquid displaced equals to volume of the object. So which means feel free to use it here, 5 times 10 raised to minus 5. To make this easy for you, convert it to what? Some standard form, power over 10. This times 10 raised to minus 3. This is 5 times 10 raised by what? Minus 5. So how many times can 5 go in 44? That's 8 times. So you have what? 8.9 times so there you have what? When you use the law of indices here, that's going to be what? 10 raised to the power of 2. So this is 890 kilogram per meter cube, right? So what does that mean? If you divide that by 1000, that's going to mean the RD, that's the RD is what? 0.what? Wait, let's check that out properly. 1, 2, 3. So this should be 8.9 times 10 raised by what? 2. So we have that. This is supposed to be 0.89. Did I manage that well? Kilogram per meter cube, 0.89. That's supposed to be 0.89, or what am I doing wrong there? Oh, I see. That is not 8.9. This is 89. So this is 8900. If divided by 1000, that's 8.9. So you are very much what? Right with that computation. You get that? The one that has what? 8.9 is copper. So your computation is right. Let's take another example. So we'll take another example. Okay. Now we have a question on thickness. So I'll make this question to be 40 seconds. I want you to use 40 seconds for this. Okay, I'll count 40 seconds. I want you to attempt it. 10, 20 seconds, 30 seconds, 40 seconds. I'll add more 10 seconds. Time up. No one provided an answer to this within the timing. Oil of mass 0.5 kg and relative density 0.5 forms what? A thin film of area 0.25 meter cube on the surface of water. So the thickness of the film is what the question is from you. For you to understand this better, let me try and diagnose something. So say we have a container. Is a container, and on the container you have what? In the container you have a liquid, water to be specific. Then according to the question, you then have what? Oil on the surface. I want you to understand this. That's why I am diagrammatizing it. So this is the oil standing on the liquid. So it has what? A thickness. Let's call the thickness of the oil, let's call it T. That's what the question is from you. The mass of the oil is supplied as 0.5. The density of the oil you also know. The relative density is given as 0.5. Automatically the density is 0.5 gram per cm cube. What will you use this information to get? Of course, that will be the volume of the oil. From density being mass over what? Volume. You can tell that what? Volume should be equal to mass over what? Density. So what would that be? 0.5 gram divided by what? 0.5 gram per cm cube tells us that the volume is 1 gram per cm cube. Sorry, the volume is 1 cm cube. So if the volume is 1 cm cube, they give you the area of the what? Of the film. That's, let's look at the top surface of the film. Let's say the film has what? A circular cross section. So right now we need the thickness. You know, thickness, volume should be equals to the thickness times the cross sectional area. So in this case, the thickness is going to be the area, the volume divided by the what? Cross sectional area. Since our volume is 1 cm cube, 1.0 cm cube, divided by the area. Now you will notice that the area was supplied in meter cube, so you need to do some conversion, either taking the area to centimeter square or taking the volume to meter cube. Let's work with the volume. The volume is 1 cm cube. The word centi means 10 raised by minus 2. So I have 1 times 10 raised by minus 2, all in a cube, divided by, what do you have? This is now meter cube, divided by 0.25. So you can choose to use your calculator for that. So you have 1 exponential minus 6 divided by 0.25. So that gives you 4 times 10 raised by minus 6. So this is 4 times 10 raised by minus 6 meter cube. Sorry, that will now be meter, not meter cube. So which is what you have as option D. And this is me solving this question in a way you should understand it. Now, if I were to be a candidate in the exam hall, first thing is to read the question and understand it. Let's say it's going to take you about 15 seconds max to do that and process it. From here alone, you can tell that what you can get volume of the object, and based on what you can see, you can use the eye inspection to do the volume, like 0.5 divided by 0.5. So that gives you the volume as what? 1 cm cube. And you know that you get your thickness by dividing by your area, 0.25 meter square. Now, based on what you have here, you can tell that the units are not in agreement. This is cm cube, this is meter cube. So you have centi is 10 raised to minus 2, then all cube 10 raised to minus 6 divided by 0.25. Boom, you press your calculator and get your result. That's how you are meant to solve this problem as a candidate in the exam in order to save time. Alright, let's do 3 more questions. Uh, 3 more questions. Okay. Okay, we have a question here. So I'll give 40 seconds max for this question. 40 seconds. And your time starts now. Ten seconds. Twenty seconds. 30 seconds. 40 seconds. What is happening? You guys are not active enough. It doesn't make sense not solving questions like this in 40 seconds. Doesn't. This is 2 meter cube. I'll wait for 10 more seconds. This is really poor. Very, 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 very poor. What could be your excuse that you can't solve this problem? Doesn't make a sense at all. So we have a 2 meter cube of a liquid X density given. It means with 3 meter cube of density Y. Question is asking for the relative density of the mixture. What do? You first get the density of the mixture itself. Density of a mixture is equal to mass of mixture over what? Volume of what? Mixture. Mass of mixture is not given. From density equals to mass over volume. Mass is what? Density times volume. For X, the mass is given, density and volume are given. So we have 2 times what? 1 times 10 raised by minus, 3. Then plus for y, we have 3 times what? 0.8 times what? 10 raised by 3 divided by what? The sum of the what? 2 volume. This is 2 plus what? 3. So there you have to use your calculator. So, but you can do without calculator here. This is 3 times 0.8 is 2.4. 2.4 plus 2, that's 4.4. 4.4 divided by what? 5. So that's what we have there. So we have 4.4 divided by 5, or divided by 5, that's 0.88. 0.88. This is 0.88 gram per cm cube, or we have 880 kilogram per meter cube. So I've already told you that RD of a substance is also going to have the same magnitude with the density of the substance. The difference would be that the RD we have no unit, while the density of the substance in gram per cm cube has a unit. RD and density in gram per cm cube always have the same magnitude. So the answer is 0.88. Like I said, it doesn't make sense you not solving this question in less than 40 seconds. It doesn't make sense. So you need to practice more and ensure that you can solve questions like this in less than 40 seconds. Okay, so for you that you do not understand that, because I just have to be fast as possible solving that, let me explain that again. Density of a mixture, density of a mixture is going to be mass of the mixture over volume of the mixture. So in this case, they are talking about x and y. That will be mass of x plus mass of y over volume of x plus what? Volume of y. So in the question, they have supplied the mass of, they didn't supply a mass of x, but mass of x is going to be density of x times volume of x, from density equals to mass over volume. Mass of y is going to be density of y times volume of y. So we can then say that this is density of x, volume of x, plus what? Density of y, volume of y, divided by what? Volume of x plus what? Volume of y. So you can then insert in the information supply. The density of x was given as 1 times 10 raised by 3, while the volume of x is given as 2. So this will give you 2 times 1 times 10 raised to the power of 3. Then plus, for y, volume is 3, density is 0.8 exponential 3. So we have 3 times 0.8 times 10 raised to the power of what? 8. 3, sorry. Then divided by 2 plus 3. Mind you, the information we have on top is going to be a kilogram. What we have below is a meter cube. To make computation easier, factor out 10 raised by 3. So you now have 2 plus 3 times 0.8 is 2.4, because 3 times 8 is 24. Then divided by 5. So this is like saying 1000 times 4.4 over 5. So look at it, keeping the 1000 and just focusing on 4.4. How many times can 5 go in 4.4? 0 times, because 5 is bigger than 4.4. Now, how many times will 5 go in 44? That's what? 8 times. Because 5 times 4, 5 times 8 is 40. We are left with 4. In 40 again, that's 8. So this is 880 kilogram per meter cube. Convert it to gram per cm cube by dividing by 1000. That's 0.88 gram per cm cube. You can now get the relative density, and I told you already that density of a substance in gram per cm cube is also going to mean the RD. It's going to give you the exact result of the RD. So this is what you have there. This is me showing the solution explicitly. So more question. So I want us to solve a problem where we may have to use okay, let's see, okay, hold on, let's take a new question. Okay, let's copy that. More pages. Now look at this, everyone. Okay, attempt that. I'll give 30 more seconds. Time up. Say that again. Okay, you got 13 Newton. All right. So okay, good. Let's set B. Nice. Let's find out. Yes, I can hear you. That's correct. Let's find out if it is correct. Okay, thank you very much. 13 recorded. All right, let's see. We are looking for upthrust. They gave us the weight in air to be 50 newtons. So that they said it displaces 3.7 kilogram of water. It displaces 3.7 kilogram of water. You are falling for the trap. They gave you water. So mass of water displaced, mass of liquid displaced is given as 3.7 kilogram. Then that means weight of liquid displaced, if we take G as 10, it's going to be 37 newtons. Okay, that is the situation. Weight of liquid displaced being 37 newton. Don't forget that according to Archimedes, upthrust is what? Weight of liquid displaced. That is 37 newton. So you are wrong. It is not 13 newton. The answer is what? 37 newton. You fell for a trap there. The answer is 37 newton, not what? 13 newtons. All right. We'll take one more question, then we'll call it a day. Okay, hold on. I've seen one. 2. All right. Control. Yep. So here, now look at this. Okay, I want you to attempt it. I'll give 30 seconds. Time up. Say that again. 0.3. Did you say 0.3 or 0.03? Okay, let's find out. So the question say a solid weighs 720 Newton in air. Weight in air is 720. Sorry, 750. And 525 Newton when completely immersed in a liquid. Weight in liquid 525. It says we should look for the volume of the what liquid. Volume of the liquid. Okay, we can easily calculate upthrust here. Upthrust is equals to weight in air minus weight in liquid. This is 750 minus what? 525. So what was that going to be? That was what? 225 Newton. That's the upthrust. And according to Archimedes, upthrust is also equals to weight of liquid displaced. And when you break this down, that's going to be okay. That's going to be what's it called? Density of the liquid, volume of liquid displaced times what? G. Okay, now watch. We have upthrust. We need the volume of the solid. Volume of the solid will also be equal to volume of the liquid displaced. So once we get volume of liquid displaced here, we are good to go. Our upthrust is 225 newtons. Density of the liquid is given as 0.75. 0.75 also means 0.75 gram per cm cube, or simply 750 kilogram per meter cube. What I'm using here is the SI unit, so we have 750. Then times G, let's take our G as 10. So you have 225 divided by 750 divided by 10. So you are very much right. The answer is what? 0.03 meter what? Meter cube. Right. On this note, we're gonna call it a day. Thanks for listening and bye.